Alright, here I'm going to talk about lab exercise 7. We're looking at the Earth-Sun relationship. We're going to be focusing on heat energy that's driving Earth processes that comes from the Sun and that we call sunlight. A couple of factoids that you can go ahead and put in your notes are the Earth, there's about 1.3 million Earths could fit inside the Sun, just to give you some perspective. 109 Earths could line up across the Sun's equator. The Sun's mass is about 330,000 times that of the Earth. Gravity is F of g is equal to g, this very teeny tiny constant, times m1, m2. Those are just two masses divided by the radius squared at some distance from each other. This is what provides the force keeping the Earth in orbit. And technically, the Sun is orbiting the Earth as well. It's just not as pronounced. It's much more massive. So here we have the Earth-Sun relationships. So we have to recognize that the Earth is moving. It's rotating. Right, the Earth rotates around an internal axis. This is what leads to day and night. In this picture here, we can see that the side facing the Sun would be daylight, and side facing away would be nighttime. So here I have darkness, here I have light. It's illuminated. So the term illumination implies that the Sun is reaching it and we're talking daylight. If it's not illuminated, it's darkness. So we call that nighttime. So here I have a revolution. And in the picture we see the counterclockwise orbit of the Earth to the Sun as well. So we have this counterclockwise rotation, we have this counterclockwise orbit as well. So because the Earth has an axial tilt of 23.5 degrees, different locations on Earth receive different amounts of direct sunlight. And we can see that in the picture. I want you to observe the axial tilt is relatively constant here in this picture. And in this case right here, we'll go ahead and start with the summer solstice. The northern hemisphere, the Tropic of Cancer, is receiving the most direct sunlight. It's getting the greatest insolation. Therefore, 23.5 degrees is going to have what we call the greatest heat density. And as a result of this, northern hemisphere is experiencing summer. And therefore, the contrary is correct as well. Southern hemisphere is in winter. If I pay attention up here to the Arctic Circle, this is experiencing 24 hours of daylight, and the Antarctic Circle is experiencing 24 hours of darkness. So here I move from summer into my fall equinox. I move into winter solstice. Notice the polar region here is complete darkness, and the southern pole, the North Pole, complete darkness, and the South Pole is complete sunlight. And the Tropic of Capricorn is receiving the most direct sunlight or insolation. It'd be perpendicular from the observer on the surface, and we would say it's 90 degrees above the head, and more importantly, we have the greatest heat density here. So northern hemisphere is in winter, and then here we go to our spring equinox. And during the equinox, we have 12 hours of daylight and darkness. Okay, so I want to make sure we have a chance. In the picture, you should be able to see or make sense as to why both of the tropics have significance, that they are found at 23.5 degrees north and south. And really it's the maximum sun angles just kind of oscillating back and forth between 23.5 north and 23.5 degrees south. And so the tropics, these named lines that we have, they're pretty relevant. They're pretty significant to the Earth. So here I'm looking at Earth-Sun characteristics, that we will say that the Earth is located on average at 93 million miles, 150 million kilometers from the Sun. That the Earth-Sun distance is referred to as 1 AU, or 1 astronomical unit. And this value changes due to the Earth's elliptical orbit around it. It actually changes by about 5 million kilometers, or roughly 3 million miles, plus or minus. So here's a picture, and this is a highly exaggerated elliptical orbit. Right? We learned that Kepler's first law says that all objects that are orbiting in some elliptical shape, and we'll be looking at Kepler's second law here very shortly. But this is definitely an elliptical orbit, not this pronounced, so this is exaggerated. And here I can see that the Earth is closest, or at perihelion, where in this case it calls it periapsis, which is fine, those are synonymous. In early January, we would say January 3rd, it is the closest it's going to be. But ironically, the northern hemisphere is experiencing winter. So it's not a function of being closer to the Sun, it's a function of being the directness of sunlight. And then notice where we have aphelion, or away, in this case it's called apoapsis. Once again, synonymous. This occurs during the first week of July, or early July, July 3rd, some places I've read say July 4th. But in this case, we've got this closest distance, perihelion, we have this furthest distance, aphelion, and we can kind of get an idea as to what's taking place as the Earth is orbiting the Sun, as gravity is kind of holding it in this orbit. So moving on here, the seasons are not based upon the distance from the Sun. Instead, seasons are the result of the directness of sunlight an area receives. And I'm reiterating this distance here because in July, when we're furthest away, Northern Hemisphere is experiencing summer. And that is the result of the directness of sunlight, as I've mentioned a couple times. So here I can see, I want you to pay attention to these red lines. The red lines are going to be identifying heat density. So if I have the incoming rays, right, rays are what we'll call straight lines that radiation travels in. The energy from sunlight is not spread evenly over the Earth. One hemisphere is always dark, which we call nighttime, and receiving no solar radiation at all. On the other side, or the daylight side, only the point directly under the Sun receives the full intensity of solar radiation. From the equator to the poles, the Sun's rays meet Earth at smaller and smaller angles, and the light gets spread over larger and larger areas. And these are what we'll look at here. So this date right here, I could say, if I know that the heat density is along the equator, I could say that this is at or near one of the equinoxes. And in this case, as I travel further, I want you to see that the red lines are being more spread out. In other words, we could say a couple different things. We could say that the directness of sunlight is much more directly overhead at the equator. We can assume that that would be an equinox because we know that time of year is when it receives the greatest directness of sunlight. We're looking at heat density. The heat density would be greatest where the insolation, the incoming solar radiation, is at its closest to perpendicular 90 degrees. And as I travel further or towards the poles, it gets spread out, it gets distributed, therefore it has a lower density. The red lines indicate the different amount of heat density reaching the Earth's latitudes. So, incoming sunlight angle. Here's an important one. So, the more direct the sunlight angle, the more power, which we'll refer to in watts, an area receives per unit area. An area is going to be measured in meters squared. So in the picture, closer to the sunlight angle of 90 degrees, or directly overhead, receives more energy per unit area, meaning a greater value of watts per meter squared. And I'm looking at this picture here. This is saying that it's happening kind of somewhere close to being directly overhead, and this would be more of a polar region where it's a lower angle. So it's comparing a 73 degree angle to that of a 26 degree angle. And you can see that it's much more spread out when we talk about that area being spread out over a polar region. That this amount of power that we'll refer to as watts per meter squared gets spread out, in this case, at 2.24 meters squared, whereas at a much more direct angle, it's only spread out over 1.04 meters squared. So here we're talking just a greater density of heat. And we're referring to this term as insolation, incoming solar radiation. And this is the term that is summarized as insolation. And this is really going to be the term for the rest of this unit. The lower the angle of insolation, the less power an area receives. So we can say that the greater the insolation angle, the greater the heat density. So here's a scenario we can consider. So at 40 degree north latitude, that's close to us in the Chicagoland area, where obviously we'd be 42 degrees north. Let's call it, this is close enough. So I want you to observe the perceived arcs from June 21st, the summer solstice, right, our longest day, to an equinox, right, where the angle is going to be a little bit lower, and lastly to our winter solstice, on December 21st, where it's going to be the lowest angle of the year. And I want you to observe that the angle and the arc of the sun change. That this is based on the Earth's both the axial tilt and the relative position of the sun during its orbit. So we perceive the sun traveling, moving through the sky, but it's really the Earth that's moving. We're viewing the sun from a moving platform. So the movement is actually simply us viewing it from the sun's position as it's rotating. So if I take a look here, we can calculate the angle by using what's called an Analemma chart. And the Analemma charts can be very, very important, and I'm simply just going to brief you on it right here. That we're going to want to make sure we know how to interpret these dates to find the declination along my y-axis. So, and then we can use this simple equation, noon-sun angle is equal to 90 degrees minus, we find, or provided the latitude, plus or minus declination. And our declinations are found here. So the plus or minus is simply going to be depending on the hemisphere that we're solving for. We'll add if they're on opposite, and we'll subtract if they're on the same hemisphere. So I can do this. I can say, and go ahead and solve this if I know the let's see, what do I know? I know the date and I know the latitude. Yeah, here's my latitude. And so therefore I can apply this, and it gives me enough information to be able to solve this here. So let's do a practice run. So this one here was for 40 degrees north latitude. So let's take a look at this one. Let's solve it. So I set it up. So what is the noon-sun angle? So here's my equation. Here's an example picture, location 40 degrees north. So what is the noon-sun angle, NSA, for a city at 40 degrees north on January 28th using the Analemma chart? Now, I know you can't interpret this, but you'd find that January is up over in this top corner over here. And we would find it, let's see, where did I just lose it at? Scratch that, it would be in the bottom right corner. And we would find January 28th right over in here. And you would find that, I believe it's hard to interpret this, I think it's the declination of 18. Yes, it is. So what is the noon-sun angle for a city 40 degrees north on January 28th using the Analemma chart? So it's over here, excuse me. So find the declination using the provided date. And I found the declination to be 18. So I'm simply just setting it up by plugging it in this equation. So set up and solve for the known latitude plus or minus the declination. Add if they're on opposite hemispheres, and subtract if they're on the same hemispheres. Well, 40 degrees north is in this hemisphere, and the declination is in this hemisphere at 18, so I have to add them. So 40 plus 18, I get 58. 90 minus 58 is 32 degrees. I would say that, or I would know that the sun angle is going to be 32 degrees on this particular date, on January 28th, at 40 degrees north. So that's just a little practice problem. And here I can get into using the Analemma. The Analemma chart allows you to calculate the noon-sun angle. You'll subtract if it's on top of the Analemma chart. It's not necessarily on top. I guess same, and you subtract if they're on the same hemispheres, and you'll add if they're on opposite. So be careful. This is in reference as to most of the time I give you references that you'll be solving from that are in the northern hemisphere. Not always the case. So you subtract if it's the same and add if it's the opposite, and that's always a true statement. So seasonal changes in insolation differ at any given time. So what we can do is we can find this, knowing that this noon-sun angle is 90 minus latitude plus or minus declination. You can go ahead and pause this and try these on your own, and you can see that I have the answer key down here. But it's probably good practice. It's worth your time, and that'll only take you a second. I need to get into this. Why does the Analemma look like a figure 8? Right, this picture is a very distinctive figure 8. So here goes. If the Earth's orbit around the Sun was a perfect circle, the eccentricity value would be 0. And if the Earth had no axial tilt, the Sun would appear at the same position at the same time of the sky, at the same time of day throughout the year. The Analemma curve would be but just a single dot. But if the Earth's orbital path was circular, its current axial tilt would generate a symmetrical figure 8 of the same size. But the Earth's path is elliptical, and that the Earth travels at a greater speed at perihelion when it's closer than aphelion further. So that's just quick revisitation here. We can apply this to Kepler's second law, that when it's closer, it's traveling faster. It's got to make sure it keeps up the law of equal areas, that this equal area, this pizza slice, is the same area as this pizza slice. So when it's closer, it has to be traveling faster to make up for the area. When it's further, it travels slower because it has such a larger radius. So we could say that very confidently that the Earth's orbit is a result of the the Analemma itself is a function or a result of the Earth orbit, the Sun, in an elliptical path, and has an axial tilt of 23.5 degrees. That together, these both lead to the figure 8 Analemma chart. And the last topic I want to get into, and you can pause this and look at this yourself, you'll want to read these, but I'm getting close to the end of my time here. I want to make sure that you realize you know how to interpret this, that if I look at the times, the different latitudes are experiencing different amounts of daylight hours, and therefore daylight and darkness. We've got 24 hours, so you can interpret this on your own. I want to make sure we get a chance to interpret what's going on with Langley's, that the poles themselves are very important, and they actually receive complete daylight hours. They're getting a lot more Langley's than any other